Hi, here is a problem for two-dimensional Coulomb's law. So we've got multiple charges in a situation. We want to know the total force felt by one of those charges. I have done this problem before in a video, but now I'm redoing it with a way to do the math that's a little bit easier. You don't have to do so much trig with sines and cosines. You just use this cool similar triangles and the math just kind of pops out. It's awesome. So let's do this. I want to know what is the net force on this 6 nanocoulomb charge. All right, first up, I always like to say, what is that feeling? Let's just draw the forces because that'll give me a sense of the final direction of the force. All right, I am this -6. What do I feel from a -4? It's going to be repelling me, so it's pushing down. So the force from the 4 is going to be pushing downwards. And what is the force of the +8 doing? Well, it's going to be attracting me upwards. So the force of the 8 is going to be up that direction. So my final net force should definitely be going to the right. I'm not sure if it's going to be up or down. I don't know. I don't know. We'll find out. So let's do this. We are going to use Coulomb's law to figure out what is the force of the 8 acting on the 6, what is the force of the 4 acting on the 6. Let's do this 8 acting on the 6. Coulomb's law. Okay, our constant, 9 times 10 to the 9. And charge 1 is 8 nanocoulombs. Charge 2 is 6 nanocoulombs. What's the distance between them? Dang it, why do I always pick the angled one first? So we have to figure out the distance between them. Draw a triangle, 7 centimeters here, 6 centimeters here. What is that going to be? Well, the Pythagorean theorem tells me it's going to be 9.22 centimeters. All right, so distance between the 6 and the 8 is 9.22 centimeters. Got to convert to meters, 0.0922. And then don't forget to square it. If we do this, the 8 on the 6, I get an answer of 5.08 times 10 to the -5 newtons. All right, so there's the force of the 8 on the 6, and we know the direction is up and to the right. Next, let's do the force of the 4 acting on the 6. 9 times 10 to the 9, our constant. And the charge is 4 times 10 to the -9, 4 nano, 6 nano. What is the distance between the 4 and the 6? That is this. Convert centimeters to meters, 0.07. Don't forget the squared. And what do you get for this one? 4 on 6. I get 4.41 times 10 to the -5 newtons. In what direction is that? Pointing straight down. All right. So we've done Coulomb's law to figure out the two individual forces acting on the 6 nanocoulomb. We know that the 8 is pulling it up with this strength, and we know the 4 is pushing it down with this strength. To get the net force, the total force, what that 6 feels overall, we need to add these two as vectors. And here is where my awesome little math trick comes into play. We need to know what the x component is. We need to know what the y component is so that we can add those components together. We know that the direction of this force of the 8 pulling on the 6 is exactly the same angle as the distance between the hypotenuse of this triangle. The angle that it's pulling at is the same as the angle that this hypotenuse is at. So I can draw a similar triangle for forces. And what's, okay, 5.08 newtons times 10 to the -5. I'm going to ignore that for now. I want to know what the x component is, what the y component is. I don't have to do the angles. I don't have to do sines and cosines. All I have to do is ratios. 6 is to 9.22 as x is to 5.08. My x component is what? 3.33 times 10 to the minus 5 newtons. All right, same thing for y. 7 is to 9.22 as y is to 5.08, and my y component is 3.86 times 10 to the minus 5 newtons. And now I'm just going to put signs on to remind me, hey, I got to be careful about the signs. This is pulling up and to the right. To the right means this is a positive. Up means this is a positive. Okay, I now know the x and the y components for this. I know the x and the y components for this. Pretty easy. X is 0, y is 4.41. Now I can put them together into an x and y chart to add them all up and come up with my net force components. So I'm going to erase, and then we'll do that. All right, let's get those components into the chart. We've got two forces. We've got to figure out the x and y components for both, which we already did. So the force of the 8 acting on the 6, we just figured those out. In the x direction, it is a positive 3.33, and all of the exponents are the same, so I'm going to shortcut writing those down. Y was positive 3.86. In the other force, we've got left, right, there's nothing. And all of that force is downward in the negative y direction. I think that was 4.41. Yep. All right. So let's add them up. Wow, this is easy. I can do this one in my head. 3.33. Positive. And this one, I don't want to do that in my head. We get negative 0.55. All right, I know the total left-right force, and I know the total up-down force. I'm going to walk 3.33 to the right, and then I'm going to go down 0.55. Oh, let's move that 3.33 where it won't be in the way. Okay. Then, net force is going to be the hypotenuse of this triangle. 3.33 squared plus 0.55 squared equals F net squared. The net force, the size of the force, the total force acting on the 6 is, what are we, 3.38. And don't forget to put those exponents back in, times 10 to the minus 5 newtons. Don't stop there. Because forces are vectors, we need the direction. So let's figure out what that angle is. The angle is going to be the inverse tangent of 0.55, opposite over adjacent, 3.33. And I get an angle of what? Oh, 9.4. So about 9 degrees. And that is, again, how do I want to describe this? If I just told you it was at 9 degrees, I'd probably think start at 0 and go 9 degrees up. So 9 degrees alone doesn't tell me, it's like, is it 9 degrees from here? Is it 9 degrees from there? Where is it? So you could do it, let's see here, at negative 9 degrees, right? Go start at 0 and go down. You could do it at positive 351 degrees. You could do 9 degrees south of east. That would work. Or 9 degrees below the positive x-axis. So the total answer is going to be this size of force at this direction. However, whichever one of these makes sense for your brain. So that is one way to do these problems that doesn't involve as much trig. It's just taking advantage of similar triangles. Now next I am going to say, what is the force on the 8? All right, so we've already calculated the force of the 6 on the 8. We know those components. All we have to do is figure out the 4 acting on the 8. So I'm going to erase, and we'll figure out what the total force acting on the 8 is. All right, let's figure out what the 8 is feeling. So what is the 8 feeling from this 4? I am a positive. There's a negative over here. It's going to be pulling me. So the force of the 4 is going to be going to the left. All right, and I'm just going to do that real quick up here. The force of the 4 on the 8. 9 times 10 to the 9. 4 nanocoulombs. acting on 8 nanocoulombs. And again, don't include the positives and negatives in the charges because Coulomb's law is technically, it's the absolute value. It only gives you the size, not the direction of the force. Okay, what's the distance between the 4 and the 8? 6 centimeters. 0.06 meters squared. All right, the force of the 4 on the 8 is, what do we get for that one? 8 times 10 to the negative 5 newtons. And what direction? That is going to the left. All right. I can dump that directly in here. There's no up-down component, and it's all in the negative x direction. So negative 8.0, 10 to the minus 5. All right. Now, I'm not going to do all the work of figuring out the force of the force of the 6 acting on the 8. Because I, just in the last problem, solved for the force of the 8 on the 6. Newton's third law says 8 on 6, 6 on 8 equal opposite directions. So the 6, what's it doing to me? It's attracting me down. Yep, which makes sense. It's got to be the opposite of this. So the force of the 6 pulling on the 8 down and to the left. I know the numbers already. I just need to worry about the direction. Okay, down and to the left. Ta-da! That was easy. Here we can do our sums. Got a negative 3.86 and negative 11. Yep, I can do math. 11.33. All right, here is the total horizontal pull that the 8 feels. Here is the total vertical pull that the 8 feels. Let's slap them together into a triangle. So we are going to walk 11 to the left, and then we're going to walk 3 down, 3.86 down. What we want is the hypotenuse. Net force, and we need to know that angle. Net force, we'll get 3.86 squared plus 11.33 squared equals net force squared. Pythagorean tells me that the net force is, we're looking at about 12 newtons. And what is the direction? Our angle is the inverse tangent of 3.86 over 11.33. And I get what? 19 degrees. Okay, so the force is 12 newtons at, okay, so we could do 19 degrees south of west. We could do a positive, so we start at 0, 90, 180 plus 19. So positive 199 degrees. You could do 19 degrees below the negative x-axis. What else could you do? I guess, yeah, you could do it at a, I don't know, 360 minus that, a negative, but why would you do that? So let's just stop there. All right, so we have the total force that the 8 nanocoulomb charge feels. And it is down and to the left, which makes sense because we have left and we have left and down. So total has to be down and to the left, and that's it. It's nice and fast and easy. I hope you enjoy this new method of doing these problems. I'm loving it, so I hope you love it too. Thanks for watching.